So in this first video, I'm going to begin by providing a little bit of background context about the problem that we'll actually be using to motivate our software within this lab. And if you're not an electrical and computer engineering major and you're not comfortable or you haven't seen RC circuits before, it's really irrelevant. All that we need is a function and use case in engineering program to kind of teach how one would go about segmenting a software workflow into functions and scripts and kind of doing some diagramming techniques along the way. And I always like to do a lab like this in engineering program early on, not necessarily focused on the formal methods to utilize these techniques in software design, but just to introduce the principles. So in case you're not familiar with what an RC circuit is, it looks like this. And just to give you a little bit of background information, this is the schematic symbol. Schematic means just a universally agreed upon symbol used to denote a particular type or model of an electrical component of a DC voltage source. And they don't actually look like that. Schematic symbols aren't intended to be photorealistic. In practice, this is something like a battery, or it's something like a charger that you plug into the wall. On the plug-in side of the wall, that's actually AC voltage or alternating current voltage. And voltage is distributed in AC because in order to get power over a long physical distance from the point at which it's generated to your house, it's more efficient from an energy point of view to use alternating current voltage. However, anything in your house that operates using transistors, which is anything that satisfies the von Neumann architecture of a computer or anything that has an analog amplifier in it, it typically will require DC voltage in order to operate. So it's kind of an interesting situation in the sense that you need AC to distribute over long distances, but you need DC to be useful within your house. So this could be a battery, it could be a solar cell, it could be the output of any plug-in or charger or converter that you have plugged in. And then these two components are ideal resistors and capacitors. And resistors do exactly what it sounds like. They resist the flow of electrical current. From a physical point of view, they take the energy that's provided to them and they convert that to heat. And the capacitor actually takes energy that's provided to it and it stores it in an electric field. And these have tons of different applications in electronic circuits, but it's not overly important. All that I need you to know is that in a traditional circuit, right, it's a closed loop through which charge or current can flow. If you look at the schematic symbol of a capacitor, you can kind of tell that inherently it is an open circuit. And in fact, that's how it achieves its energy storing capability. You have two conductors separated by some material that doesn't conduct electricity. Maybe it's air, maybe it's plastic or something like that. So what happens is, in terms of the current in this circuit, if you put a DC source, meaning the polarity of the push never changes, you're not going to have a long-term current in this circuit. Basically, what's going to happen is enough charge is going to move through the circuit after the switch is closed, and the switch is doing nothing more than giving us a context of the time at which our simulation is beginning. But after that switch is closed, all that's going to happen is enough current will flow to charge up this capacitor until the voltage across the capacitor equals the source voltage, and then everything interesting in that circuit is done. And that initial period of charging the capacitor is called its actual transient period. And after the capacitor has been fully charged, that is referred to the steady state period of operation of this circuit. So if you look on the actual diagram that I gave you, and hopefully I won't make a mistake on this, the current in this circuit as it varies over time, and this is all referenced from t equals 0, being the point at which the actual DC source is attached, is going to be whatever that source value voltage is, divided by the resistance value in the circuit. And if you just look at that, hopefully everyone has seen before, this looks a lot like Ohm's law. This would be the current you would have in the circuit if the capacitor was just shorted out, if there were no capacitor in it. And this kind of scaling value multiplies exponential decay function e minus t divided by tau, where tau is a time constant that is simply the product of the resistance and capacitance. So if you didn't get any of that physics, just note that what we're going to try to do today is kind of demonstrate the principles of software engineering workflows in order to develop a function that can compute this current value for different values of R and C. So that's a really good candidate for a function because we're kind of taking a block of code and we're segmenting it into a single file. In that particular file, right, we can have well-defined inputs. In this case, the resistor and capacitor values, and well-defined outputs. In this case, a vector corresponding to the values of the current in that circuit. So that's exactly what we're going to do here in problem 1, is think about, when we think about functions, how do we actually kind of document them as we're going about the process of trying to write our software. And maybe you've seen in mathematics this idea of representing functions by a block diagram. And the block diagram of the function basically denotes kind of the mechanism of how it works. You put in an input, which is some value within its domain, and then you generate an output. So this is kind of a one-to-one function, one input, one output. And that output is said to be in its range. So in software engineering, the kind of process looks quite the same. However, so I'll kind of put SE for software engineering down here. You often call the inputs that you're passing to the function an actual set of parameters. And one of the most confusing things as you're getting started with functions, and we talked about this a little bit in the lecture module, is the number of parameters can range from 0, this is kind of uncommon, to a much larger amount. I mean, I don't want to get into the theoretical basis of how large it could be, but you can have functions that take 5, 10 input parameters and so on. The output here, the key thing to know from a software engineering perspective is that all functions don't necessarily produce an output. They typically do, right? We typically view them as a black box that you're going to pass some input variable parameters in, and you're going to produce some input variables, some output variables rather, on the out of the function, on the output of the function. However, just keep in mind that functions from a software engineering point of view can have no inputs and they can produce no outputs, but they generally will do. So the first question that we want to do here, if you read what we are trying to do up here in the problem description, we want to write a custom function to plot the variation in the DC current of a general RC circuit over time, and then build a script to basically call that function and test it for multiple particular RC circuits. So how would a function block diagram look? What are we trying to do here? Takes as input the 3 basic circuit parameters and returns the value of the current over a time period corresponding to 5 time constants. So from an actual functional point of view, what we're trying to do is to code up this function inside a black box. And if you notice, it says that what we want to do is feed in as input parameters the 3 characteristics that kind of differentiate, sorry, I was too zoomed in there, one RC circuit from the other. So in practice, R will be a particular value measured in ohms. Maybe it's like 100 ohms, or maybe it's 1,000 ohms. The capacitor will have a particular value that is measured in farads. Typically, a farad is a very large unit of capacitance, so that's really going to be scaled by some kind of metric prefix. Maybe it's like a microfarad, or maybe it's a nanofarad. And in addition, there will be some particular value of DC voltage that's connected to the circuit. So this is a general RC circuit, and we define particular RC circuits by picking specific values of VS, R, and C. So that's what I mean by this function is going to take as input these 3 parameters, VS, R, and C. So this is my function here. And when you take, and we'll even do this a little bit as we move later on in the course, there are kind of specific standards for diagramming workflows or what you're trying to do in software engineering. But for now, just view it as a box where on the left, you put your input parameters. On the right, you actually put what the function is producing. And if you go back and read in the Word document, what we're trying to do is take as input the 3 basic circuit parameters and return the value of the current over a time period of 5 time constants. So we want to produce the current here, and it wants to be over a time period. And I'm just going to write 1, 2, 5 tau. And you can use whatever notation you need in order to make it make sense to you. But here, when I look at this, I say, hey, I want to write a function that takes these 3 values as inputs, they're all scalars, and produces a vector that is the output of the current for the first 5 time constants. And the physical relationship that I'm going to need is this function up here. I of t equals Vs divided by R, e to the minus t divided by tau. So in addition, usually on this type of block diagram, you will actually pick a name for your function. So I'm going to call this compute. Now remember, there's kind of 2 valid identifier techniques that you can use to define either variable or script or function names in MATLAB. I like to prefer to write my things in camel case. And camel case just means that anytime you go to a new word, rather than putting a space, you capitalize that next letter. That way you can actually easily draw to your eye what you're trying to say. So I'm going to say this is compute RC current. That's the valid and good name that I produced for my function. You can write it on top, you can write it on the bottom, but in general, this is what I would like to see you all, as you're starting to think about how you write up your functions, turn something in similar to what I've circled right there, where I can see I'm going to have a box. It's going to take as input these three variables. It's going to use this formula in order to produce this output. And here is a valid name for it. It's valid because it contains only letters, numbers, and underscores. That is particular syntax for the MATLAB language. And it starts with a letter. It's good because it's descriptive of what this function is actually doing. So that's kind of like how a function block diagram would work. In addition, I think it's important when you're starting to lay out an anticipation whenever you're going to write a function in any software language to think about how it will actually look. Particularly here, if I were to plot this current, and we're going to see an example of this when we get to the next portion of the lab and we actually talk about validating it. So traditionally, if you look at this function, again, going back to what the switch is meaning in this schematic, this is showing you that you're really only going to consider values of time, plotting values of time for t greater than or equal to 0. And hopefully everyone remembers in this exponential function, regardless of what r and c are, which will determine what tau is, when t equals 0, this becomes e to the 0. E to the 0 is just 1. So this means that at t equals 0, this will take on a peak value of vs divided by r. And then since tau is always going to be positive, since r and c are positive values, this will just be an exponential decay function. And what we're going to see, so this is asymptotically going to approach a horizontal asymptote of the horizontal axis here. And what we will see when we actually, the reason that I picked this 5 time constants is after 5 time constants, I don't want you to remember the actual number because this isn't an actual physics or circuits class, but just know that the current is effectively 0. So in terms of what you're turning in for that first little block there, I'm just looking for basically your first functional block diagram. And the reason that you want to do all this, you might say, well, why is he going through all this stuff and not giving us specific rules of how we actually have to go about diagramming our work? I'm really trying to emphasize 2 things here. Good coders, before they actually start to code, use pencil and paper and write out what they're actually planning to do. And when you have, another thing is, even though you could, depending on who you have for your software engineering class and what actual books you use and whatnot, there might be different kind of expectations or standards for how you actually go about diagramming things. Since functions by definition are little code blocks that take inputs in general, they might not, but usually they do, and they produce outputs in general, and they do it according to using some rules. In this case, our rule is a physical law. This type of diagram, of a block diagram that shows or lists your inputs on the left, shows your output on the right, has your kind of governing law inside, and then has the name of the function above, is going to be like a very effective diagramming tool when I actually start to code and just to make sure that I'm staying on track. So 2, write basic pseudocode of the function for the input-output configuration assumed above. What decisions will you have to make as the function designer? So what do I mean by pseudocode? So pseudocode in general just means, so you can kind of think of it like this. So hopefully everyone has seen this word before. If you haven't, you get a new word today. So pseudocode. And I think I totally spelled that wrong because when I write on my DocCam here, you can probably see I have to kind of bend at a weird angle. Yeah, actually it looks kind of right. I'm impressed with myself. So it's a little bit tough to write on the DocCam and keep eye contact and stay close to the speakers and whatnot. But kind of think of pseudocode like this. If this is how we talk, like using complete sentences and maybe being grammatically correct depending on who we are and who we're talking to. So here is kind of the way that we communicate to each other. And here's actually our code that has to follow the particular syntax rules of the language. Pseudocode, for some reason it was very easy to write there. Pseudocode is going to be somewhere in the middle, right? It's going to be closer to code than natural language, but really what it is doing is trying to break down the process that you're trying to code up in a step-by-step fashion. So we know that we're going to take as input these 3 values. So usually the majority of pseudocode styles that you see, they'll start by listing the inputs. So I'll say inputs, VS, R, and C. And you might ask yourself, well, when I actually code this up, How am I going to name those variables? Clearly, I can't have a subscript, but I could just call a variable v sub s. That is valid syntactically in MATLAB. It only contains letters. And it's a good variable name because it actually makes sense, because relative to the problem we're trying to solve, people will understand what VS means. They'll understand what R means. They'll understand what C means. You might say, well, maybe I'll name my variable resistor. Well, you could. That's a valid variable name, but and it is certainly more descriptive explicitly than just using an R. But there's always a trade-off when you, and it's kind of related to your own personal style as a coder, when you pick variable names between having things that are descriptive, which will have a lot of characters, and having things that are compact. So anytime in general that you can have compact variable names and they're still meaningful and they're still explainable, it's good coding practice to use those shorter variable names. So here are our inputs. Usually you list your outputs at the top. So the outputs are going to be the value of the current, ranging from 1 to 5 time constants. So remember that MATLAB is a discrete programming language. So what you're going to have to do if you want to use this function is written in continuous notation. T is a continuous variable of time defined from 0 theoretically all the way up to infinity. So we're going to have to actually create a vector of time for which we're going to compute these values that is discrete. So that's actually the first step that we need to do. We need to define our discrete time vector. And that's not really good pseudocode here. That's kind of getting into like a little bit of a comment. Usually, so this is what we need to do. So put it in parentheses. I wouldn't actually put this in your pseudocode. How are we going to do it? Well, think about all the different techniques that we talked about to define vectors within MATLAB. We talked about, so let's go over here for this, defining vectors in MATLAB. We talked about a technique where you could explicitly list all of the values in the vector. So if we got to go all the way from 0 to 5 tau, we could go 0, and I don't know, maybe we need to, what about if we just make them spaced by 0.1? So I'll make this 0.1, I'll make this 0.2, and so on and so forth. That's probably not going to be a good way to do it, right? Because depending upon the value of tau, you're going to have a lot of individual keystrokes where you're having to explicitly define the elements in the vector here. So that's probably not going to be a good approach to define the time vector for which we're computing the actual time values. Instead, we probably want to either use the colon-based operator that we spoke of or the linspace-based operator. And I'm going to choose to use the colon here. You could use the actual, you could use linspace if you wanted. So say I use colon operator and I went T, I needed to start at 0. And then I'm just going to call this next increment between the elements in my vector space for now. And I'm going to say it needs to go up to 5 tau. So that's what I mean by in your pseudocode, what you're actually having to define that's not explicitly said. Since you're working in a discrete time programming language and not a continuous time programming language, you have to pick the steps between the individual values of time for which you're computing this current. So my pseudocode, right, again, you probably don't want to have this is way too descriptive. It sounds like how we talk in sentences. I would have something like this. Step 1, compute their delta t value. And I would say, I mean, it's probably a good technique if you think about it. You might say, well, maybe it should be 0.1 and maybe it should be 0.01, or it's probably not a good thing to hard code. If you know you're going to define this for 5 time constants, and this is something that you have to play with, I would actually start to define delta t as some function of the time constant. So I would say like as tau divided by 10. And what that's going to ensure is that I have at least 10 samples for each time constant range. And you can always turn around and once you generate and validate your code, change that particular number here. Well, in order to have this be well-defined, what are you going to need? You're going to need to first define tau. So you might say tau, you'll define it from those inputs as R times C. So tau equals RC, and then we'll have, and usually you won't write even compute here in pseudocode. You would just have tau equals RC, delta t equals tau divided by 10. And really, I want to be clear here though. I'm like giving you rules of how to write pseudocode. There are no rules. Unless you're like in a class and your professor says, hey, your pseudocode has to be written this way. Really what you're trying to do is to write something between how we talk that's kind of natural conversational language and the actual syntax. Because if you look here, I'm kind of getting too close to the syntax. So it's kind of a trade-off. It has to be useful to you. And really individuals, the longer they code, the more their pseudocode looks like actual syntax and the less it looks like how we talk. So I'm curious to see, there's no right answer for that. I want to see how you would go about documenting step by step of how you would actually make this computation in your function. So I'm going to, in mine, I'm going to define tau first, then I'm going to compute delta t, and then I'm going to have my discrete value of times for which I'm computing the current using Coulomb notation is 0. I'll step by delta t, and I'll go up to 5 tau. And then I'm going to compute my actual current value using this formula. So I have I equals Vs divided by R. And then I will just use the exponential function. And then I will take my values of t for the vector. I will divide by tau, and I'll make that computation. And then I will simply return I. So return is a common word that you see in pseudocode that basically is just saying, hey, that function's over now. So the key elements I would like to see in your pseudocode, make sure you have your inputs and outputs listed at the top. Make sure you show me the process by which you will use this formula. In order to use this formula, you have to define discrete values of time to make the computation, and you have to define what tau is, and make sure you show me what you're actually returning. In this case, you're returning, and I should do a little bit better there, the current from 1 up to 5 tau. But if you notice here, if we only define t over this range, naturally, I here in the computation is only going to be defined over that range as well. So you can just say return I. So I'm not going to post these notes, that way no one actually just kind of copies directly what I have, but that is what I'm looking for here. Some kind of block diagram to show me that you understand the basics of what a function does. It takes inputs, it produces outputs according to some rule. Also have a syntactically valid name that makes sense for your function selected. You probably don't want to use the same one as mine. Just pick a new one. And then 2, maybe you could just not make yours camel cased, and you could use underscores to emphasize the spacings in the new words. And then 2, I'm just looking for the basic pseudocode. You can use whatever style you want, but again, make sure you have inputs and outputs at the top and list what you're returning, and give me a logical flow of how you would go from those inputs to those outputs, realizing that MATLAB is actually a discrete language, of course, like all anything that doesn't have a symbolic toolbox like Mathematica, or there is a symbolic toolbox in MATLAB. We will talk about it in this class. So since we're working in the discrete domain, show me how you will generate the discrete values of time in a vector for which you'll compute your current.